Now let's discuss the models, right? The actual models. So if you look at the models for information diffusion, they are broadly categorized into two types. The first type of models is called decision based model, right? In the decision based model, the idea is that you basically look at your neighbor's adoption strategy, and based on that you have the liberty to decide your strategy, okay, whether you adopt a particular product or decision or not, right? You have the liberty, you have the freedom to decide. Whereas the second type of model that we will discuss later is called probabilistic model. Probabilistic model, and here the idea is that you don't have control on the adoption process. With certain probability you will adapt, otherwise not, right? Now decision based model is mostly applicable for situations where you want to be a part of a certain protest, you want to buy a product, you want to go for a movie or not, you want to go to a restaurant or not. It all depends on your decision, you have the freedom. Whereas probabilistic model applies to cases, for example, disease spreading, epidemic spreading. Now when users interact, right, two individuals come closer to each other with certain probability, and say one user is already infected, with certain probability the other user will also be infected, right? The other user doesn't have the liberty to choose whether he will be infected or not, right? So this is probabilistic model. So we will discuss about the probabilistic model later, but now we will focus on the first type of models called decision based model. So let's look at the process, right? So given a network, each node has the freedom to decide whether to adopt a particular contagion or not, right? Remember, the contagion can be a product, an opinion, an individual, and decision, right, and so on. Originated from the idea of local interaction models, right? Basically depends on how you interact. We will see that we mostly look at two-party interactions. We will not look at the other interactions as a whole. We look at a two-party interaction, and based on that we decide. Decision at each node is influenced by the behavior of nodes in its neighbors, right? We already mentioned that depends on your neighbor's decision. Nodes decide to adopt a new contagion driven by a direct benefit or a payoff. Now this is very important. So let's say, let's take the same example, right? Subscribing to Netflix versus Amazon Prime. Now whether you subscribe to Netflix or Amazon Prime, it depends on your profit, benefit, right, or payoff. It's called payoff. In the game theory literature, it's called payoff. Now if you see, say if you are more of a Bollywood kind of movie lover, you may want to choose, you may want to subscribe to Amazon Prime because of the amount of collection compared to Netflix, right? Whereas if you are, say, more of a Hollywood kind of movie lover, you may want to subscribe to Netflix rather than Amazon Prime. It depends on your payoff. The payoff can also be measured in terms of money, right? Say if you subscribe to Netflix, you will have to charge, you will have to be charged, say 2,000 per month. I don't know the subscription charge, but let's say 2,000 per month, right, or 2,000 per quarter. Whereas Amazon Prime, say the charge is whatever, say 1,000 per quarter, right? Now you want to choose Amazon Prime rather than Netflix, right? So the payoff by adopting a particular contagion is directly proportional to the number of its neighbors that have already adopted the same contagion, right? So the idea is that, let's say, let's take another example. Let's say there are two voice communication apps. One is WhatsApp and other is Skype, right? Now which one you would like to choose? Now you would look at your neighbors, right, your friends, and you see that most of your friends have installed WhatsApp, right? So, and you also want to communicate with your friends quite often, quite frequently, so you would also install WhatsApp, not Skype, right? It depends on your neighbor's decision, neighbor's choice, right? So, it can be explained using a two-player coordination game. Now, we will discuss this thing later. So, in game theory, there is this famous two-party game or two-player game, multiplayer game and so on. So, in two-player game, you may have heard about something called zero-sum game, right? Now, here we will not talk about zero-sum game, but here the idea is that we assume that there are only two parties, two individuals, and one individual has already adopted something and the other individual will decide his strategy depending on his friend's strategy, right? And at the end of the day, what's the objective function? What you want to maximize? You want to maximize the payoff, right? So, given a number of strategies, the end goal of the players is to coordinate on the same strategy to maximize their payoff. Okay. Now, this will be clear in the next slide. Okay. Let's say you have two strategies. Strategy 1 is subscribing to Amazon Prime. Strategy B is subscribing to Netflix, right? Now, let's say you are you, okay, and V is your friend. So, V has already adopted A, right? Strategy A. If you also adopt A, the payoff would be A, small a, right? Now, this payout would basically be benefit, some sort of benefit. Okay. So, both U and V, they have adopted the same strategy A and both will get a payoff A. Let us say V has adopted B and U also has adopted B, right? The payoff would be B. A, B, these are constant, small a, small b, these are constant, some sort of payoff that will decide. Okay. V has adopted A and U has adopted A. Sorry, V has adopted B and U has adopted A, right? So, the strategies are different, therefore, the payoff would be 0, right? And the other way around, V has adopted A and U has adopted B, payoff would be 0. So, let us say a game where you look at individual, you look at a two-party interactions, right? And if both the strategies, if the strategy of both the players is same, then it would be either A or B depending upon the choice of the strategy. If they are different, then 0, right? P fraction of neighbors have adopted strategy A. Now, this set of neighbors have adopted strategy A and the remaining 1 minus P fraction of neighbors have adopted strategy B, right? So, if U adopts A, what would be the total payoff? So, U's payoff would be, now remember, for each of this adoption, right, you will get a payoff of A, small a, right? And how many such links are there? There are P times D links are there. Okay. So, total payoff would be A times D times P, right? If U adopts B, then the total payoff would be B times D times 1 minus P, right? Now, what is the criteria in terms of AB, right? So that U would adopt A, strategy A. So, the criteria would be this would be greater than this. If this payoff is greater than this, then U will adopt strategy A, right? So, A times P 1 minus P, right? So, if you calculate, this would be Okay. So we are not considering the equals to condition, this is a borderline. So P, which is the fraction of neighbors who have adopted strategy A, this would be greater than this fraction B by A plus B, okay, which is also quite obvious. What is this fraction? This fraction is essentially, so B is the payoff if you adopt B, and A plus B is the total payoff. So this fraction would be greater than the fraction of payoff if you adopt strategy P, right? Let's look at an example, and this is called, this threshold is often called as activation threshold. Okay, let's look at this example. So this figure, A, I and G, they are kind of showing hard immunity, hard behavior, and they have already adopted Netflix, right? And the remaining users have adopted Amazon Prime, right? So now let's look at how the remaining users would change their strategy. Let's look at this guy, right? B has 2 neighbors, and let's say the activation threshold is 0.5. So if 50% if 50% or more than 50% of your neighbors have adopted a strategy, you would also adopt the strategy, right? So let's say node B, right? So 50%, you see that 1 out of 2 neighbors has adopted Netflix, so B will also adopt Netflix, right? What about H? 100% of neighbors have adopted Netflix, so H would adopt Netflix, right? What about C? Again 50% has adopted, so C would also adopt Netflix. So you would get this kind of setting. Now let's look at the remaining iteration. The remaining iterations, you see that for K, majority has adopted Amazon Prime, so K would not change, D would not change, E would not change, and so as F. So this would terminate, this would stop at this point, at this kind of stage, okay? Okay. Now let's look at a bit different game. Here you can choose both A and B at the same time, okay? So you can actually choose multiple strategies. Now what would be the payoff in this case? So the payoff would be as follows. Say if your neighbor has chosen payoff A and you have chosen A and B, so your payoff would be A, right? Let's see here, let's see this payoff table. Say you are you, right, and V is your neighbor. V has chosen A and U has chosen A and B. So the payoff would be A, because you won't get benefit of both A and B, because your neighbor has only adopted A, right? Let's say you have both Skype and WhatsApp, but your neighbor has only WhatsApp, right? So you can only communicate through WhatsApp, you can't use Skype. Similarly, if V has chosen B and U has chosen AB, the payoff would be B, right? If both have chosen A and B, right, the payoff would be max of A and B, okay, which is quite obvious, because say you have chosen Skype and WhatsApp, your neighbor has also chosen Skype and WhatsApp. Now you want to get benefits of either WhatsApp or Skype, right? And say you are currently in a state where WhatsApp is allowed, Skype is not allowed, so you would use WhatsApp. You are say currently in another city where Skype is allowed, WhatsApp is not allowed, you would use Skype, right? So it would be max of A and B. But important point to note is that when you choose both A and B, you will incur some cost, some additional cost. This cost is C, small c. Now this cost can be in terms of additional money. This cost can be in terms of additional bandwidth that you need to use when you use both A and B and so on. So the net payoff would be max of A comma B minus C, because C is the cost that you need to incur when you adopt both A and B. Okay. Now this cost is irrespective of your neighbor's decision, right? It depends on your decision. If you adopt both A and B, you would need to incur a cost irrespective of what your neighbor has chosen, right? Now this is very important. Remember this particular thing, constant. Now let's look at a particular setting. Let's think of a infinite chain network, right? It's an infinite chain network, right? A chain network with infinite number of nodes, and let's say small a, the payoff A is 3, the payoff B is 2, so A greater than B, and let's assume that this is a single choice game. You can't adopt both A and B, right? Essentially you are following this payoff table, and remember, so memorize this payoff table. Okay, if both the payoffs are same, you get either A or B depending on the strategy. If they are different, then you get 0. Okay. So, and let's say these two nodes, the leftmost two nodes, they have already adopted A, kind of hard behavior. They have already adopted A, and the remaining nodes can decide what to adopt, right? So let's look at this node U. Okay, so this is U, and U has two neighbors. This guy has already adopted A, this guy has adopted B. Okay, now if U adopts A, what would be the payoff for you? Payoff would be, for this interaction, payoff would be A, and for this interaction, payoff would be 0, right? So 3 plus 0 equals to 3. If U adopts B, then for these interactions, this would be 0, and for the other one, this would be B. So 0 plus 2, it would be 2. Okay, so this is maximum. This is higher than this one. So node U will choose A, right? So the strategy now has moved from this node to this node. Similarly, when you look at this node, same thing will happen. This guy will also move from B to A, right? Switch from B to A. So the strategy A will move here, and so on and so forth. So over time, you will see that all the nodes will adopt A and it will stop. Okay. Let's look at a multiple choice strategy. Okay, and remember, we will follow this table. Okay, try to memorize it again. If I choose A and my neighbor has chosen A, I will get A. If I choose B, my neighbor has chosen B, I get B. If I choose AB, my neighbor has chosen A, I would get A. I choose AB, my neighbor has chosen B, I will get B. I choose AB and my neighbor has chosen AB, I will get max A and B, max A comma B, but I will incur a cost A. In fact, in last three cases, I will incur a cost C, right? Cost C, not A, cost C, and C is a constant. Okay, let's see the same setting. A equals to 3, the payoff B equals to 2, and the cost is 1. Let's look at this node. Okay, so this is A and this is B. Okay, So if this guy if this guy chooses A, right, due to this interaction it will 3, this due to this one this will be 0, so 3. For B 0, 2, 2. If this is AB, then what would happen? Due to this interaction it will get A, which is 3. Due to this interaction it will get 2, but since U has adopted both the strategies, it will incur a cost C, which is 1, so the net would be 4. Okay, remember one thing, this cost is age independent. It means that when we look at this interaction and when we look at this interaction, this would not happen that we will incur a cost here one time, and when you look at this interaction you will again incur a cost on that time. This would not happen. Okay, so this cost is independent of the interaction. You will incur cost only one time. Okay, so this guy will adopt AB. Okay, now let's see what happens. Okay, now let's see what happens with V. Okay, so node V has 2 neighbors. This guy has adopted B, this guy has adopted AB already. Okay, we have seen. If V adopts A, then what would happen? Due to these interactions it would be 3A, small a. Due to this it would be 0, so 3. If it adopts B, 2 plus 2, right, 4. Okay, B payoff, small b payoff. For this you also get small b payoff. What about AB? For this you get max of AB, max of A and B, which is 3. For this you get B, which is 2. For and you will also incur a cost, right, 1. So this would all be 4. So you see a tie here. Okay, so since V has already adopted B, now V is choosing. Now V will not switch the strategy, because there is no point in switching. If V switches, then we will get the same payoff, right? So we will not switch. Okay, so ultimately what would happen? We'll see that the cascade, the AB cascade, actually would stop at this point. It would not move further. With this setting, the cascade AB's cascade would not move further. Okay, it will stop here. All right, so now let's look at another setting, a different choice of payoffs, different values of payoffs and cost. Initially, in the earlier case, A was 3, B was 2, C was 1. Now A is 5, B is 3 and C is 1. Okay, let's see what happens. 5, 3 and 1. So let's see for U, the same setting. So if U chooses B, due to these interactions it would get B, small b payoff, which is 3, and due to this interaction it will get 0, so 3. If U chooses A, due to these interactions it will get 5, due to this it would get 0, therefore 5. If U chooses AB, due to these interactions it will get 5, due to this interaction it will get 3 and cost is 1, so total is 7. Okay, so you will adopt AB, the same as earlier, right, with different payoffs, but that's fine. You will adopt AB. Let's see what happens with V. Now remember, this is now AB. Okay, this is now AB. So if if node V chooses strategy B, due to this interaction it would get 3, due to this interaction 3, so 6. If it chooses A, due to this interaction it would get 5, due to this interaction it would get 0, so 5. If V chooses AB, due to these interactions, this interaction, it would get max A B, which is 5, due to this interaction B, which is 3, and cost is 1, so 7. So here you see that the base strategy is AB. So B will switch from B to AB. Okay. So if B will switch to AB, then similarly for this node it will also choose AB, and so on. But now interesting point to note is that let's see what happens with this guy U, because now for U has 2 nodes, 2 neighbors. This guy has adopted A and this guy has adopted AB. When I calculated earlier for U, the setting was different. Now we have a different setting. Let's look at whether U would still retain AB strategy, or you would now move, you would now switch. Let's see. Okay, so let's look at U, right? Let's draw it separately. Okay, let's use a different color. This is U, AB. U has adopted AB earlier, and this is A, this is AB. Okay. If U has adopted, say if U switches from AB to A, what would happen? If it is A, then due to this interaction, it would be 5. Due to this interaction, this would be also 5. Right? So payoff is 10. What about B? If this is B, then due to this one, this is 0. Due to this one, this is 3. Right? Small b, 3. What about AB? The current strategy? Due to this one, this would be 5. Due to this one, this would also be 5. But the cost 1, so 9. Right? Interestingly, see here carefully, the base strategy is A. So initially U has switched from B to AB. Now when one of its neighbor has switched from B to AB, he or the node U will now switch from AB to A. Right? So in the next iteration, this would be A. So AB will move. Behind AB, A will also move. So all the nodes will switch from B to AB, then from AB to A. Right? It only happened because of the choice of A and B, payoff A and B. Right? It's very interesting. Remember this. It happens because of the choice of A and B. Initially, we have seen that we have different choice of A and B, and we had got a different result altogether. And now we have got a different result. Okay. We stop here, but I strongly suggest you guys to remember this. This payoff matrix, right? And how we choose the strategies. Okay. In the next lecture, we'll see how we can make this thing generalized, irrespective of the choice of A and B, because in a real situation, think about it, in real situation, we may not know the exact value of A and B, right? When you devise a setting, devise a model, you have to choose you have to consider a generic value of A and B, and depending on that, you have to decide certain choice and let the user, let the person assigns A and B, and automatically your strategy, your model will be adopted. Okay. So in the next lecture, we will discuss how we can generalize these two settings. Okay. Thank you.